Hello everyone, this is Dr.D.Ch.PapaRao and I welcome you all to my presentation on sequences. Before starting my presentation, don't forget to subscribe my YouTube channel Mathematics SKBRC and click on the bell icon for watching new videos. Now I want to discuss on the topic sequences. Sequences are very useful in deciding the continuity of a real valued functions on a subset of R. The chapter sequences is divided into 4 parts. In part 1 video, various types of sequences are introduced and supported by suitable examples. For the benefit of students, for easily understanding the concepts, I have provided complete solutions to problems and proofs for theorems. Definition of a sequence. A sequence is nothing but a mapping which is defined from a natural number set n. If A is a non-empty set, then the mapping or function Sn to A is called a sequence. A sequence S is said to be a real sequence if the codomain A is subset of R. If S is a sequence, then it will be denoted by the following manners: S1, S2, S3 and so on Sn, or Sn, n is 1 to infinite, or curl brace Sn. Nth term of this sequence. Let S be a sequence, then the image Sn of n is called the nth term of this sequence. It is denoted by Sn. It is shown in the diagram. Since the sequence Sn equal to S1, S2, S3 and so on, where S1, S2, S3 are the terms of the sequence Sn, here S1 is the first term of the sequence, S2 is the second term of the sequence, S3 is the third term of the sequence and so on. S1 is the image of 1, S2 is the image of 2, S3 is the image of 3 and so on. Sn is the image of n. How to define a sequence? A sequence is usually described by a set of one or more formulae for Sn in terms of n. Define Sn equal to n square if n is odd, Sn equal to n cube if n is even for all n belongs to n, where n is the set of natural numbers which is starting from 1, 2, 3 and so on. Suppose n is odd, Sn equal to n square for all n belongs to n. S1 equal to 1 square equal to 1, S3 is equal to 3 square 9, S5 is equal to 5 square 25, S7 is equal to 7 square 49 and so on. Suppose n is even, Sn equal to n cube. S2 is equal to 2 cube equal to 8, S4 is equal to 4 cube is 64, S6 is 6 cube is 216, S8 is 8 cube is 512 and so on. The set of the above two formulae defines the sequence completely. Therefore, sequence Sn equal to S1, S2, S3 and so on. This gives Sn is equal to 1, 8, 9, 64, 25 and so on. This is the sequence. How to find first few terms in the given sequence? Sometimes the nth term Sn may be given in terms of a relation involving a few preceding terms together with an adequate number of initial terms. Initial terms means the terms S1, S2, S3 and so on. Now we find the first 5 terms in the given sequence. S1 equal to 2, Sn plus 1 equal to half into Sn plus 2 by Sn for all n belongs to n. Given S1 equal to 2, which is the first term, by using this term we will find the second term S2. Put n is equal to 1, we get S2 is equal to half into S1 plus 2 by S1. Here S1 equal to 2, that is equal to half into 2 plus 2 by 2 is equal to 3 by 2. Put n is equal to 2, S3 is equal to half into S2 plus 2 by S2. Here S2 is equal to 3 by 2. That is half into 3 by 2 plus 2 by 3 by 2 is equal to 17 by 12. Similarly, we get n is equal to 3 gives S4 is equal to 577 by 408. Put n is equal to 4, S5 is equal to 665857 by 470832, which is the fifth term of the sequence. Try to find the first 5 terms in the sequence S1 equal to 1, Sn plus 1 equal to 3 into Sn plus 1 for all n belongs to n. Very important definition, range of a sequence. Let Sn be a sequence where n belongs to n is a natural number. The terms of Sn are S1, S2, S3, S4 and so on. The set of all terms of Sn is called the range of Sn. Therefore, range of Sn is equal to set of Sn such that n belongs to n, that is equal to S1, S2, S3 and so on. Example, find the range of the sequence Sn equal to 1 plus minus 1 whole power n for all n belongs to n. If n is odd, minus 1 whole power n equal to minus 1. If n is even, minus 1 whole power n is 1. For n is equal to 1, S1 equal to 1 plus minus 1 whole power 1 equal to 1 minus 1 is 0. For n is 2, S2 is equal to 1 plus minus 1 whole square equal to 1 plus 1 equal to 2. For n is equal to 3, S3 is equal to 0. For n is equal to 4, S4 equal to 2 and so on. The range of Sn equal to set of S1, S2, S3, S4 and so on, that is equal to 0, 2. These are only distinct elements. The remaining terms are repeated. It is a finite set, also bounded. Finite sequence. Let Sn be a sequence where n belongs to n. A sequence Sn is said to be a finite sequence if the range set of Sn is finite. Example, every constant sequence is a finite sequence. Since the range of a constant sequence is a singleton set, so it is a finite set. Hence, the constant sequence is a finite sequence. Example 2. Consider a sequence Sn equal to 3 plus minus 1 whole power n for all n belongs to n. For n is equal to 1, S1 equal to 3 plus minus 1 whole power 1 equal to 3 minus 1 is 2. For n is equal to 2, S2 is equal to 3 plus minus 1 whole square equal to 3 plus 1 is 4. For n is equal to 3, S3 is equal to 2. For n is equal to 4, S4 is equal to 4 and so on. The range of Sn equal to S1, S2, S3, S4 and so on equal to 2 and 4. 2 and 4 only distinct elements. It is a finite set, also bounded. Hence, the given sequence 3 plus minus 1 whole power n is a finite sequence. Infinite sequence. Let Sn be a sequence. Sn is said to be an infinite sequence if the range set of Sn is infinite. Example 1. Consider Sn equal to minus 1 whole power n into n for all n belongs to n. The terms of Sn are S1 equal to minus 1, S2 equal to 2, S3 equal to minus 3, S4 equal to 4, S5 equal to minus 5, S6 equal to 6 and so on. Range of Sn equal to set of S1, S2, S3 and so on, that is equal to minus 1, 2, minus 3, 4, minus 5 and so on. It is an infinite set and unbounded. Hence, the sequence is infinite sequence. Example 2. Consider Sn equal to 1 by n for all n belongs to n. The terms of Sn are S1 equal to 1, S2 equal to 1 by 2, S3 equal to 1 by 3, S4 equal to 1 by 4 and so on. Range of Sn equal to set of S1, S2, S3, S4 and so on equal to 1, 1 by 2, 1 by 3, 1 by 4 and so on. It is an infinite set and bounded. For large values of n, 1 by n tends to 0. That is 0 less than 1 by n less than or equal to 1 for all n belongs to n. It is an infinite sequence. Constant sequence. A sequence Sn is said to be a constant sequence if the range set of Sn is a singleton set. That is, range contain only one element. If Sn equal to k, for all n belongs to n, k belongs to r, then the sequence Sn is called a constant sequence. Example, Sn equal to 10 for all n belongs to n is a constant sequence. Here S1 equal to 10, S2 equal to 10, S3 equal to 10, S4 equal to 10 and so on. Range of Sn equal to set of S1, S2, S3 and so on equal to 10. Only one element is a singleton set. Example 2. Define S1 equal to 3, Sn plus 1 equal to 1 plus 2 root Sn minus 2 for all n belongs to n. For n is equal to 1, S2 is equal to 1 plus 2 root S1 minus 2, S1 is 3, that equal to 3. For n is equal to 2, S3 is equal to 1 plus 2 root S2 minus 2, that is 1 plus 2 root 3 minus 2 is 3. For n is equal to 3, S4 is equal to 3, n is equal to 4, S5 equal to 3 and so on. Sn equal to 3 for all n belongs to n. Therefore, Sn is a constant sequence. Fibonacci sequence. If a sequence Sn is defined by S1 equal to 1, S2 equal to 2 and Sn plus 1 equal to Sn plus Sn minus 1 for all n belongs to n and n greater than or equal to 2, then the sequence Sn is called a Fibonacci sequence. Given that the first term S1 equal to 1 and the second term S2 equal to 2, take n is equal to 2. We get S3 is equal to S2 plus S1 equal to 3 by using S1 equal to 1, S2 equal to 2. Put n is equal to 3, we get S4 is equal to 5. Put n is equal to 4, we get S5 is equal to 8 and so on. Therefore, the sequence Sn equal to S1, S2, S3 and so on equal to 1, 2, 3, 5, 8, 13, 21, 35 and so on. Here 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21, 21 plus 13 is 35 and so on. This is the Fibonacci sequence. Each number is equal to the sum of the preceding two numbers in the sequence. The subsequence. Let Sn be a sequence. A sequence Tk is said to be a subsequence of Sn if for every k belongs to n, there exists another sequence nk belongs to n such that n1 less than, n2 less than, n3 less than and so on, and we write Tk is equal to Snk for every k belongs to n. Therefore, subsequence of Sn equal to Tk is equal to Snk. Here n1 less than, n2 less than, n3 less than and so on, then the sequence nk is strictly increasing sequence. How to define a subsequence? Example, consider a sequence Sn equal to n for all n belongs to n, where n is a set of natural numbers. For n is equal to 1, S1 equal to 1. For n is equal to 2, S2 equal to 2. For n is equal to 3, S3 equal to 3 and so on. The sequence Sn equal to set of S1, S2, S3 and so on, that is equal to 1, 2, 3, 4 and so on. Consider a sequence Tk is equal to 2, 4, 8 and so on. That is equal to 2, 2 square, 2 cube and so on. Clearly, it is a subsequence of Sn, where Tk is equal to Snk and Nk is equal to 2 power k for every k belongs to n. And k is 1, 2, 3 and so on. For k is equal to 1, we get n1 is equal to 2 power 1 is 2. For k is equal to 2, n2 is equal to 2 square equal to 4. For k is equal to 3, n3 is equal to 2 cube is 8. K is equal to 4, n4 is equal to 4, 4 is 16 and so on. Clearly, n1 less than, n2 less than, n3 less than and so on gives sequence nk is strictly increasing sequence. Therefore, subsequence of Sn equal to Tk is equal to Snk is equal to 2, 2 square, 2 cube and so on, which is the required sequence. One more example. Define the nth term of the sequence Sn equal to 1 by n for all n belongs to n. Since n belongs to n gives n is 1, 2, 3, 4 and so on. For n is equal to 1, S1 equal to 1 by 1 equal to 1. N is equal to 2, S2 equal to 1 by 2. N is equal to 3, S3 equal to 1 by 3. N is equal to 4, S4 equal to 1 by 4 and so on. Therefore, sequence Sn equal to S1, S2, S3, S4 and so on, that is equal to 1, 1 by 2, 1 by 3, 1 by 4 and so on. Consider a sequence Tk is equal to 1 by 5, 1 by 6, 1 by 7, 1 by 8 and so on. Clearly, it is a subsequence of Sn where Tk is equal to Snk and Nk is equal to k plus 4 for all k belongs to n. For k is equal to 1, n1 is equal to 1 plus 4 is 5. For k is equal to 2, n2 is equal to 2 plus 4 is 6. For k is equal to 3, n3 is equal to 3 plus 4 is 7. For k is equal to 4, n4 is equal to 4 plus 4 is 8 and so on. Here n1 less than, n2 less than, n3 less than, n4 less than and so on. Sequence nk is increasing sequence. Therefore, subsequence of Sn equal to Snk is equal to Tk is equal to 1 by 5, 1 by 6, 1 by 7, 1 by 8 and so on, which is a subsequence of Sn. Important note, let Sn be a sequence. A sequence Sn has two subsequences, namely S2n and S2n minus 1, where 2n is even and 2n minus 1 is odd. Example, consider a sequence Sn equal to minus 1 whole power n for all n belongs to n is 1, 2, 3 and so on. If n is odd, then we get minus 1 whole power n is minus 1. That is, S1 is minus 1, S3 is minus 1, S5 is minus 1 and so on. If n is even, we get minus 1 whole power n is 1. That is, S2 is 1, S4 is 1, S6 is 1 and so on. Therefore, the sequence Sn equal to S1, S2, S3, S4 and so on, that is equal to minus 1, 1, minus 1, 1 and so on. S2n equal to S2, S4, S6, S8 and so on is 1, 1, 1 and S2n minus 1 is S1, S3, S5, S7 and so on is minus 1, minus 1, minus 1, minus 1 and so on. These are the subsequences of Sn. Example, we show that the sequence 1 by n factorial is a subsequence of the sequence 1 by n. Given sequence Sn equal to 1 by n is 1, 1 by 2, 1 by 3, 1 by 4 and so on, and Tk is equal to 1 by n factorial is 1, 1 by 2 factorial, 1 by 3 factorial, 1 by 4 factorial and so on. We show that Tk is a subsequence of Sn. Now we define Nk is equal to k factorial and Tk is equal to Snk for all k belongs to n, k is 1, 2, 3 and so on. For k is equal to 1, n1 is equal to 1 factorial is 1, k is equal to 2, n2 is equal to 2 factorial is 2, k is equal to 3, n3 is 3 factorial is 6, k is equal to 4, n4 is equal to 4 factorial is 24 and so on. Here n1 less than, n2 less than, n3 less than and so on, the sequence nk is strictly increasing sequence. Therefore, the subsequence of Sn equal to sequence Tk is equal to sequence Snk is equal to 1, 1 by 2 factorial, 1 by 3 factorial and so on, which is the subsequence of the sequence 1 by n. Similar example, show that the sequence 1 by n square is a subsequence of the sequence 1 by n. Here nk is equal to k square for all n belongs to n, k belongs to n and Tk is equal to Snk. Proceed as above problem. Try to solve this problem. Show that the sequence 1 by 2 power n is a subsequence of the sequence 1 by n. Take nk is equal to 2 power k for all k belongs to n. Is the sequence 1, 3, 2, 4, 8, 5, 9, 10 and so on is a subsequence of the sequence n? Comment your answer, yes or no. Using the integration of technology with this subject will provide an efficient environment in learning mathematics quickly. Here I have added some web links as quick references. They can greatly help students to encourage visual problem solving. I hope this presentation will help to students and they will more confident to attempt university semester and examinations. The remaining part to be continued in part 2 PPT video. If anyone who likes more information or has questions, please feel free to contact me at my mail ID dchp876@gmail.com. I really appreciate your support for what I do for the welfare of the students community. Thank you one and all. for listening to me so far.